In this video, we solve a homework problem that is on our written homework for the spring 2021 semester. We're asked to solve an initial value problem. The differential equation is a homogeneous, linear, ordinary differential equation with constant coefficients, and we've got two initial conditions. First, we solve the differential equation. We find the general solution, and then after we find the general solution, we use these two initial conditions to find the values of the constants in our general solution. So let's start by solving the differential equation. Since we have a constant coefficient homogeneous linear differential equation, we're going to let y equal e to the mx, because if we have an exponential function, we take its derivatives, we get other exponentials. If we have just the right exponential function, if we multiply those by constants and add them together, all the exponentials will cancel out and we'll get a 0. Since it's second order, we're going to compute y prime and y double prime as well. We're assuming e to the mx is a solution. Derivative of e to the mx is m times e to the mx by the chain rule. Derivative of e to some power is e to that power times the derivative of the inside. And then when you take the derivative again, you just get another m out front. Then we substitute into the differential equation. If y is equal to e to the mx, that's giving us an m squared e to the mx minus 4 times y prime, which would be m e to the mx in that case. And then we've got 20 times y here, and that's equal to 0. And we want to factor out the e to the mx from all of these guys. And we end up with this. Now, the exponential is never 0, so that means this polynomial must be 0. Now, if we could factor it, we would factor it. It's quadratic, so you could also use the quadratic formula, but that's not necessary this time. There are no two numbers that I can multiply together to get 20 that add to -4. So when I see this, rather than using the quadratic formula, I think I'd rather complete the square. I've got a coefficient of 1 in front of my m squared there. I've got an even number in front of the m. So completing the square is going to be relatively easy. So to start completing the square, I will subtract the 20 from both sides. I'll identify b. You want to take half of that and square it. -2 times -2 is +4. Add that to this side to complete the square. That's legal as long as you also add 4 to the other side. Now everything stays nice and equal. Then this side is a perfect square, and this side, of course, can be simplified. So -20 plus 4 is -16. And I ask myself, what two numbers can I multiply to get negative or to get +4 that add to -4? -2 and -2 will work. So that's m minus 2 squared equals -16. Now I'm trying to undo operations to get m by itself. So I want to get rid of this squaring function. To do that, I take the square root of both sides. Don't forget your plus or minus on the right. And that simplifies to plus or minus the square root of 16, which is 4 times I. And then we add the 2 to both sides. So we have complex conjugate roots. This is a quadratic characteristic equation. So we've got two roots, m1 and m2 are equal to 2 plus 4i and 2 minus 4i. So our alpha is 2 and our beta is 4. So that means our two linearly independent solutions are e to the alpha x times cosine of beta x, and another one that's just like it, but you replace the cosine with a sine. So we'll have e to the 2x times cosine of 4x, and the other one's just going to be exactly the same, but instead of a cosine, you've got a sine. All right. So we had y, we chose the right y, we computed y prime and y double prime. We substitute into the differential equation because we're assuming that y is a solution, and we simplify. And then you've got your characteristic equation here. Then you can use whatever method is necessary or appropriate to solve for m. Since it's a quadratic equation, we want to solve for m1 and m2. This time we completed the square. You could have also used the quadratic formula if you wanted to. And then once we see that m1 and m2 are complex conjugate roots, then we can use those to state the two linearly independent solutions, y1 and y2. And we want the real solutions, not the complex exponential solutions. Okay, so that's enough to get us the general solution. The general solution of the differential equation is y equals, since it was second order, c1y1 plus c2y2, or c1 times this exponential times cosine, plus c2 times this exponential times sine. And that will work for all real numbers. Okay, now if we were just asked to find the general solution, we would be done, but we were not asked to find the general solution. We were asked to solve an initial value problem. So we have to find the values of C1 and C2 that cause these to be satisfied. Basically, the way we're going to do that is we're going to come up with two equations and two unknowns, and then we're going to solve that system of two equations and two unknowns. Now, in order to get those two equations, we need y prime. The first equation involving C1 and C2 comes from replacing x with 0 and y with 2/3 here in our general solution. If I replace x with 0 and y with 2/3, the only unknowns in this equation will be C1 and C2. So we'll have one equation with two unknowns. And then we also want to do the same thing in y prime. In order to do that, we have to compute y prime. So we compute y prime, and then we replace x with 0 and y prime with negative 2/3, and that will give us an equation involving C1 and C2. Once we have two equations and two unknowns, we can solve those two equations and two unknowns for C1 and C2 using any of the pre-calculus methods, and then we back substitute C1 and C2 into the general solution to get the particular solution. Okay, so that's the plan, but that requires finding y prime. So let's find y prime. It'd be easiest to find y prime if we factor out the exponential here. So I've got e to the 2x times c1 cosine of 4x plus c2 sine of 4x. If I treat this as my first function and this is my second function, I can compute the derivative using the product rule. So that was from a different problem. Let's just use the rest of this paper. I like to use as much of the paper as I can. I go through so much paper. Let's not waste any paper. Recycle, reduce, reuse, recycle. So our y is equal to this. Okay, so when we compute y prime, we're going to use the product rule. Here's our first function, and there's our second function. So according to the product rule, we'll get derivative of the first. The derivative of e to the 2x is e to the 2x times the derivative of the inside, which is a 2. The derivative of the first times the second. Plus the derivative of the second, which I'll do in a second, times the first. Okay, derivative of the second. You bring the c1 down and you multiply by the derivative of cosine of 4x. Derivative of cosine of 4x is negative sine of 4x times the derivative of the inside, which is a 4. Okay, then we're going to add, bring your c2 down, the derivative of sine of 4x. Derivative of sine of 4x is cosine of 4x times the derivative of the inside, which is a 4. And that's our y prime. If you want to, you can simplify further. I've got e to the 2x, and then I've got times 2 times c1 times cosine of 4x. And then I have e to the 2x times 4c2 times cosine of 4x. I'm looking for the cosine terms. So from these, I could factor out the cosine function, and I'll have that product involving the exponential, the cosine, and the c1 plus c, the 2c1 plus the 4c2. And then we have another one over here for the sines. We'll have 2 times this guy there. And then for the sines here, we have negative 4 c1 times sine. Okay, so that's giving us this. We've got e to the 2x times cosine of 4x. And all of that is being multiplied by this 2c1 plus 4c2. Then we're adding that to this. We can factor out the sine of 4x here. So we'll have 2c2 minus 4c1 times the exponential times sine of 4x. Okay, so we have y prime, and we have y, and we have initial conditions. Now we can put those pieces together to come up with our 2 equations and 2 unknowns. We're going to use the first equation, or the first initial condition, to get our first equation involving c1 and c2. So the first initial condition says this: y of 0 equals 2/3. What that means is that when x equals 0, y is equal to 2/3. Okay, so I can replace x with 0 in this function right here, and then I want to simplify as much as possible. Y was c1 times e to the 2x times cosine of 4x plus c2 times e to the 2x times sine of 4x. And we're replacing x with 0. Sine of 0 is 0. E to the 0 is 1. Cosine of 0 is 1. This is also 1. So we end up with just c1 this time, which is nice. c1 times 1 plus c2 times 0, which is just c1. We'll set that result equal to 2/3. So that means that c1 is equal to 2/3. And then with the second initial condition, we have y prime of 0 is equal to negative 2/3. So that means that when x equals 0, y prime is equal to negative 2/3. So typically we would say I've got one equation with 2 unknowns, and then a second equation with 2 unknowns. So we'd have 2 equations and 2 unknowns. But this time, because of this sign of 0, that first equation, rather than being one equation with 2 unknowns, it ended up being one equation with 1 unknown, which means it's going to be easiest, pretty easy to solve for this one. Okay, so now we want to do the same thing that we did with y of 0. We want to do that with y prime of 0. So we want to write down our y prime function. Y prime is equal to this. So we have 2c1 plus 4c2 times e to the 2x times cosine of 4x plus 2c2 minus 4c1 times e to the 2x times sine of 4x. And we're replacing x with 0 everywhere. E to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. So we just end up with 2c1 plus 4c2 times 1 plus this times 1 times 0, which is 0. So this whole second part here is going to go away. It's 0. And we're setting that equal to whatever they told us y prime of 0 was. They told us y prime of 0 was negative 2/3. So you set that equal there. So now this is two equations and two unknowns. Now the first equation was really simple. It automatically gave us C1. So since we know C1, we can use that C1 in here to get C2. But in general, you would have two equations and two unknowns, and you would have to solve that system of equations. It's not always this simple as it turned out to be for that y of 0. But in this case, we just replace C1 with 2/3. And we have this. So that's going to be 4/3 over here, plus 4C2 equals -2/3. And then you want to subtract 4/3 from both sides. So we've got -2/3 minus 4/3, that's -6/3, which is -2. Divide both sides, or all three parts of this equation, by 4 to get C2. And you have C2 equals -1/2. Okay, so we know what C1 and C2 have to be because we just did that. C1 is positive 2/3 and C2 is -1/2. So once you solve that system of two equations and two unknowns, you have to substitute into the general solution to get your particular solution. So remember, your general solution was y equals C1 e to the 2x times cosine of 4x plus C2 e to the 2x times sine of 4x. And C1 turned out to be 2/3 and C2 turned out to be -1/2. If you want to, rather than adding -1/2 times that, you could just subtract that. Just to clean it up a little bit. If you want, you could factor out the exponential as well, although that's not necessary. And this function will work. It satisfies both the differential equation and both initial conditions on -∞ to infinity. Okay, so that's how we do that. It starts by solving the differential equation by letting y equal e to the mx, substituting, solving the characteristic equation for m. Since we notice we've got complex conjugate roots, y1 and y2 have this form. And then since it was a second order equation, general solution is C1y1 plus C2y2. Once you've done that, you've got to find C1 and C2. The way you find C1 and C2 is using these two initial conditions. Since the initial conditions involve y of 0, or excuse me, y and y prime, you need to compute y prime. And when we computed y prime, where did it go? Well, when we computed y prime, we got this. And then when we once we have y and y prime, we evaluate y at 0 and set the result equal to 2/3. That gives you one equation. Then you evaluate y prime at 0 and set the result equal to -2/3 in that case, because that's what the second initial condition told us to do. That gives you your two equations and two unknowns. Then you solve those two equations and two unknowns by whatever process you want. Since the first equation happened to have one equation, or happened to have only one unknown, we were able to just take that C1, substitute there, and solve for C2. Then once you have the C1 and C2, you substitute those into the particular solution, and then you clean it up a little bit. And that's how we do that. Let me know if you have any questions about that, guys.